Actually, when I was in my undergrad, as Tanya said, we did not have that kind of guidance, and
Right.
okay, what are the opportunities we can look for? But yeah,
And
that really was
I
really good.
also did my graduation from Government College of Girls, Ludhiana. So
So
there was
everybody
very
here
less
has
opportunity.
everyone just started from a normal
Yeah, yeah.
Government college, yeah. It really happened with me. Whenever in triple IT, I used to tell my graduate college, they were like, "What?" And I was like, "It's just a college in my hometown." They were like,
Right.
"Okay." So, but that's why I'm telling students, I don't think that you cannot, you know, it's nothing is special in the people. Of course, they worked hard. Maybe they landed in IITs, triple ITs, but you can also go there. Maybe not with your in
Yeah.
your bachelor's or master's in some other fields, research. So you just have to dream and work. Yeah, you can do that.
So thank you, Dr. Anjali. Thank you, ma'am. Beta, if you have any query, you can ask. Otherwise, we will go for next speaker. No? So thank you, ma'am. So our next speaker is Dr. Kanika. She is research scholar at ISER Mohali, and she did her MSc from Punjab University, Chandigarh. She has many publications in reputed journal and attended many workshops in different areas. She also worked as teaching assistant on Python programming language. She received many awards and fellowships in the field of mathematics. Uh, so I welcome you, ma'am.
Thank you, ma'am. Thank you for the introduction. It was not a great achievement, but ma'am put it like a big thing. Thank you, ma'am.
No, no, ma'am. It is a big thing to actually you are doing PhD at Kaiser Mohali, which is a very known institute.
Thank you, ma'am. Thank you. Hello, everyone. Thank you for the organizers for giving me this opportunity. Thank you, Tanya, for giving me this opportunity. Although it was a very, I did not have much time to prepare for the talk, but still I would like to introduce myself. So I'm Kanika. I'm doing research in the Job Potential Center Simple as Zebras in ISA Mohali under the supervision of Dr. Amit Kulshresht. You might have known his name, you might have heard of his name. So, being a core mathematician, I will just talk briefly about my research to show you how the small things, small group structures like groups, algebras, fields, vector spaces can lead to some very influential big results, can help us produce many big results. So you might have heard, you might not have familiar with this differential simple algebra structure, but you must have known groups, fields, rings, modules, ideals, vector spaces. So what are vector spaces? Given a field K and a set of elements x1, x2, xn, the collection of all linear combinations of the type summation ki, xi, where ki's are coming from the field, is called a vector space. Now if we replace this field K by ring R, then this vector space is called a module. And what is missing in this module is just the multiplication structure, the multiplication operation. So if we provide this also, then we call it an algebra. So it's a module with a multiplication structure, with a ring structure. So that's the group structure algebra. Now, what is the central simple part? In my research, I'll be just using this algebras over the field K. Over the field K, you all know about the center of the group Z, which you usually denote by Z. It's the collection of all the elements which commute with every single element in the group. Same in the algebra also, there is a collection of elements which commute with every single element of the algebra. And if that collection is precisely the field K where the algebra is based on, then it's known as central algebra. And you might also have heard about, some of you might have also heard about the ideals. I don't know which rank of students are there, but if you are in MSc or you have studied about rings and modules, you might have known about the ideals. So there are left-sided ideals, two-sided ideals, or right-sided ideals. So if there does not exist any two-sided ideal, then we say that the algebra is simple. So simple algebra is which has no two-sided ideal, just like simple ring. So the central simple algebra is a K algebra which is associative and which is simple, whose center is precisely K. For example, Q. Q is one-dimensional algebra over Q itself, and another example is Qx, which is two-dimensional algebra over Q, which the collection of all the rational functions over Q. Another very interesting example of the algebra is, which you all have must have been familiar with, it's M and K, the set of all the matrices of dimension n square over with coefficient space, and also this has a multiplication structure. If we have a matrix A and a matrix B, we can always multiply these two matrices. So it itself has a ring structure also. So it is a perfect example for the algebra. In fact, I'll be using these kind of algebras to do my research. So there is a very vast theory which is already known, which is associated with these central simple algebras. In our research, me and my guide, which we are working on, we are trying to generate one parallel theory for differential central simple algebras, which we are getting by putting an additional differential structure on the central simple algebras. Now, this is the plan of my job. I'll introduce some notations and definitions. Then I'll be telling you what do we mean by the splitting of differential central simple algebras. Then some transcendental extension will split our differential central simple algebras. And then I'll be talking about the order of DCSA, which is analogous to the order of any element of a group which we generally talk about. So what is a derivation? You might have heard about, all of you must have heard about the word derivation in your life. Now you must have heard the classic derivation where x prime is 1. Now it has two basic qualities, which is it is additive, that is derivative of f plus d is derivative of f plus derivative of g. And second quality of this derivation map is it satisfies Leibniz rule, f times derivative of g. You can define derivation which is independent of the fact that x prime is 1. We can have any derivation. So in general, derivation is defined like this: let A and B be rings, an additive map delta from A to B is called derivation if it satisfies the Leibniz rule. This Leibniz rule. Now, what is the differential ring? A ring equipped with this derivation map, that is delta from A to A, which is the derivative map, is called the differential or the derivation. Now, we know that for a classic derivative Qx, where x prime is 1, we have all the elements of Q. We know that all the elements of Q go to 0 under this map. So these are all the elements which are going to 0. So this is precisely Q is precisely the ring of constants of this ring Qx. So ring of constants is precisely those elements of A whose image under this derivation map is 0, and it forms a field of subfield of A, which is usually denoted by CA. Now extensions of rings, extensions of fields. So if B of A is an extension, then B is said to be differential extension if and only if the derivation of B when restricted to A behaves same as the derivation of A. Now, in analogous to the basic Galois theory, in analogous by attaching the solutions of some base field with the base field. Now attaching some solutions with base field, and then we'll get a new extension which is Galois extension. So in analogous to that, in differential algebra we have Picard-Bezier extensions which are generated by attaching, differentially generated by, with this we are not adding any new constants, that is precisely the constants of C, and if characteristic of K is 0 and Ck is algebraically closed, then every Picard-Bezier extension, every homogeneous linear differential equation admits a Picard-Bezier, which I already defined as associative K algebras, which are simple and whose center is precisely K. Now, in 1988, let K delta be a differential field of characteristic 0, then if we have the delta is a derivation on K, and it is always possible to extend this delta to any central simple algebra A. So we can always have a differential central simple algebra important application of Coulomb-Noether theorem that every central derivation is inner. So now further I move to tensor product of DCSs. Just like in any group structure, you have an operation. For Q you have Q star, you have multiplication. For Z you have addition, which makes it a group. But you also have multiplication on Z. You can have two numbers from Z and you multiply those two numbers, your answer will always be in Z. but you don't have inverses of these numbers. So z is monoid under multiplication operation. So that's how we can define another operations also. So this operation tensor product is also an operation. Some of you might have heard of tensor product, but I don't know how many of you have heard of this name, but still you can have a look at this after this talk. The tensor product, if these are two algebras, central simple algebras, differential central simple algebras, then the tensor product of these two is defined as A1 tensor A2 with derivation D1 tensor D2, where D1 tensor D2 is defined in this way. So this tensor product gives all the elements of this class, this central simple algebra, monoid structure. Now we can always replace this second algebra A2 D2 by E delta E also. In this case, we say that we are extending scalars to the extension E, where E delta E here is differential extension of K delta. So here we can set, if we are tensoring with this extension, we say that where we have MK, if we try to try to tensor it with E, then we mean that M and K tensor with E is actually isomorphic to M and E. That is, all the matrices coming as the coefficients are coming from E. So when we are tensoring our differential central simple algebra with E delta E, then we say that we are extending scalars from K to E delta E. That's how we are solving very many differential equations in this form, that extending scalars to E. Suppose you have a differential equation. Suppose you have an algebraic equation, any algebraic equation. Suppose x squared plus 1, you have algebraic equation x squared plus 1. Now you know that it does not have any root in Q, but you know that it has roots in C. So what you say is, if you want to have roots in the given field, you extend the scalars to C. You can take eta from C and then attach to Q, and then you get roots there. And you can split this equation. So that's how here these things are happening, that if we want to split